Hello everybody, welcome to this third chapter of nanoelectronics. Today we will talk about some nanoscale phenomena that are related to quantum mechanical effects. So in a way you should be familiar with some of these things we're going to talk about, as you may have seen this during your course of study in quantum mechanics. So more in particular we will look at potential wells, potential barriers, tunneling, confinement, Coulomb blockade, and we will briefly see what we mean by quantum of conductance. So let us start with reminding ourselves the results regarding potential wells. So let us consider first of all the simplest case of an infinite square potential well, like this one here, where our well goes from 0 to A. The potential between 0 and A is 0, while is infinite elsewhere. So we can demonstrate that in this situation the Schrödinger equation can be solved, and the solution is the one shown here. So the wave function is this one here, and the eigenstates energies are this one here. Just to remind ourselves, the way we solve this type of problems is based on writing our Schrödinger equation, which is in this case H phi equal E phi. In this specific case, the Hamiltonian is in the region between 0 and A, within the well, is simply given by the potential is 0 here, so this is the equation we need to solve for x between 0 and A, while for x smaller than smaller than 0, or x bigger or equal than A, phi must be 0. Okay, so is the solution of these two basically equations that allows us to then find the solution to the problem. So so as we seen on the slide, the actual solution, it takes the form of, if you solve this equation, takes the form where n is an integer and E1 is n squared E1, where E1 is as we said h bar squared pi squared over 2m A squared. Okay, and if we substitute the values of the constants at play here, and we use for the mass m the rest mass of the electron, we can write this quantity as 0. Okay, so this is now just a function of obviously A, the size of the potential well, and so if we use, we can get some values just to have an idea of how much is this E1, which is effectively the first eigenvalue of our system. So if we can make here a table A and E1, so when A is, for example, 100 nanometers, E1 will be around 3.79 10 to the minus 5 eV. When A is 10 nanometers, this will be 3.79 10 to the minus 3. When A is 1 nanometer, then this will be 0.379 eV. So as we can see, obviously, what is happening is that as we decrease the size of the well, the energy of the eigenstates becomes more and more discrete. So effectively what we are saying is that if this is our well, and the well is quite large, that is A is quite large, then the states are E1 will be quite small, and then the other second state would be somewhere here and then somewhere here. While if we start reducing now the size of the well, what will happen is that the first state now will be here, second state would be here, and the third state would be here. If we keep shrinking the size of the well, and you understand now what will happen, so the states become further and further, more and more discrete. So this is state 1, 2, 3, etc. 1, 2, 3. Sorry, 2 and 3. This result here regarding the eigenvalues of the Schrödinger solution means that E1 is the one shown is given by this value, and then E2 would be when n is equal to would be 4 times E1, and E3 would be when n is equal to 3, 9 times E1, etc. Now, regarding the wave function, if we were to plot the wave function that we've seen on the slide and that we've written also in here, so if we were to plot that, we could see that these are simply functions of this type. So the first phi1 would be simply this. So then we have phi2 would simply be something like this. Sorry, till here. And then phi3 would be something like this. So this would be phi1, phi2, and phi3. So if just to understand this a little bit better, if we plot these on the energy diagram of the potential well, so we had our diagram here, like that, and imagine this is our well. Say that this is our level E1, so this is the energy here, and this is the position, this is our 0, and this is A, So this is E1. Imagine this is E2, which is 4 times E1, and then imagine this one here is E3, which is 9 times E1. Then the wave function corresponding to the eigenstate E1 would be something like this. The wave function corresponding in this state would be something like this, and the wave function corresponding to this state would be something like this, and so on and so forth. Sorry. Let us now consider a slightly more complicated situation where now the well is actually a finite square potential well, like the one shown here. So in this case, again, we have to write Schrödinger equation, and actually we are now, in this case, we have to divide the space in 3 regions. So there's a region on the left of the well, the region where the well is located, and the region on the right of the well. So before we go through the results shown on this slide, let's have a look more in detail to remind ourselves how we actually approach this problem. So let us sketch once again this situation we are dealing with. So here is the energy, and this is the position. So we have our well here that is made like that this time, and so the height of the well, this is V0. Here is the 0 of the potential, and this point we call this minus L over 2, and this is L over 2. So we are assuming that this is the 0 of the position. So we have, as you can see, there is a region on the right, on the left, sorry, and a region on the right of the well. So we can call this region 1, region 2, and region 3, and we have to now write our to solve our Schrödinger equation for this problem, and this will now break up into 3 different problems. So for region 1 we have to write so this is our Hamiltonian. Oops, sorry. Then we have to do the same in region 2, but in region 2 now the Hamiltonian is simpler because the potential is 0. Oh, sorry again. And the third region, which is similar to region 1. And we should name, because this is a piecewise solution to the total wave function, we need to name the wave functions accordingly. So for each region 1, 2, and 3, and we need also to impose boundary conditions, and particularly that psi and psi prime, so the derivative, the function and the derivative of the function are both continuous. So basically that the wave function is continuous and derivable in every point, so it's particularly at the borders. So we need then to impose those conditions there, that for example for x equal to minus L over 2, this means that psi at psi1 at L over 2 minus L over 2 has to be equal to psi2 at minus L over 2, and also the derivative psi1 prime at minus L over 2 has to be equal to psi prime 2 at minus L over 2. Okay, and the same is done, this is for this border here, and then the same can be done for the other border condition, and this way we can solve the problem and reach the conclusion that the solutions are those represented here. And this is the total solution psi x. Now, we should mention here that if the energy we are considering is bigger than V0, then the particle effectively is a free particle. There are still some perturbations caused in the solution because of the presence of this well underneath, but effectively we are dealing with a free particle, so the solution psi would be effectively a wave. So it's not really interesting. That's why we are here concentrating to the situation where E is smaller than V0. Because this is the interesting part. So what happens when E is somewhere below V0? The energy of the particle we are considering is somewhere below V0. So in this case, psi takes this form here. So we are expecting that in region 1 the solution is an exponential function of the position. Remember that in this case x is negative, so this is an exponentially decreasing function, as it has to be, otherwise would explode the wave function. And the same is on the other side, in region 3, and while in the middle within the well we are obviously looking for a solution that is wave-like. So, as we said previously, imposing the continuity and the derivability of the solutions, we can in the end solve the problem and find some equation for the eigenvalues of our eigenstates. And in the end we can show that we end up with this result. So for symmetric wave functions, where we basically have the cos form, the eigenstates are given by this equation, the eigenvalues, are given by this equation, while for antisymmetric wave functions the eigenvalues are given by this equation, where EL is a parameter defined in this way, which, by the way, is exactly what we called E1 in the case of the infinite potential well. Okay. Now these equations look quite complex, and in order to solve them, we solve them actually graphically. This is done actually in the next slide. Here we can see a typical example. So how we do that? Well, we have to plot on the abscissa the quantity E over EL, and then we plot on the ordinate, we plot the two functions we just mentioned. We can see on the left hand side of both equations, so the tangent and the cotangent. So the tangent function is the one in green, and the cotangent is the one in blue. And the solution, the graphical solution to these two equations here, is made by plotting this square root of V0 minus E over E. and finding the intersection with the tangent or the cotangent function. And this is done here, as you can see. It is obviously much easier because since the abscissa is E over EL, it's much easier to choose V0 equal to some multiple of EL, and so we can plot the right hand side of the two equations we just saw in the previous slide, and we can find those intersections here. So for example, when V0 is equal to EL, then we have to expect simply one intersection here, and this also tells us we can estimate here the corresponding energy of the eigenstate. When, for example, V0 is 5 EL, we can expect we have 3 intersections, 1, 2, and 3, and so we can this way estimate the 3 eigenvalues, energies of the eigenstates, and so on and so forth. We should note here that there is always at least one solution to this problem, no matter how small is V0. This is quite interesting. Okay, we have a look now at the opposite case, or to the well. The opposite case would be a barrier. So let's have a look at potential barriers now. I would like here to approach this problem by looking at it from a slightly different point of view. So we've seen with the potential well how we solve the problems using obviously the standard approach. We write the Schrödinger equation, and then we have a piecewise solution to the problem, and so on and so forth. Now here I would like to show you an approach that is effectively similar to that, but allows the complete automation of the process, so it's very prone to be automated with a computer. Obviously the underlying physics is exactly the same, nothing changes. So we have here our potential barrier. As you can see, the potential is, as you can see, 0 up until this point, and then becomes V0 in region 2, and then goes again to 0 from A and onward. So this is our barrier. We divide the space in 3 regions, region 1, 2, and 3. Region 1 and 3 are effectively the same, so we should keep this in mind. And as usual, we need to solve the Schrödinger equation, that is this one here in its most general form, with a kinetic part, the potential part, and our wave function is psi x. Again, we need to deal with a piecewise solution of the problem, and for this specific case, what we do here is we consider 3 versions of the wave function psi, psi1, psi2, and psi3 for the 3 different regions. But as you can see, we decide in this case to start with superposition of imaginary exponentials. The only thing we change in all 3 cases is simply the coefficients. So for region 1, the coefficients are A and B, for region 2, C and D, and so on. It's quite interesting that here we are choosing just imaginary exponentials, because, and as we've seen in a way from in our previous example with the potential well, when the energy we consider is above V0, all solutions must be wave-like. So we would agree with this type of approach. But when the energy is below V0, in region 1 and 3, we would expect a wave-like solution of the Schrödinger equation, but in region 2 the solution should be a standard exponential solution, not in an imaginary exponential. But the formalism we are adopting here is actually taking that into account, because if you notice, in region 1 k is k1 and k1 is given by this. In region 2 the k value is k2 and k2 is given by this quantity. And as you can see, when we are in the situation where E is smaller than V0, k2 becomes an imaginary number, and so the exponential becomes actually a real exponential. So everything works well in this formalism. Now, in this case here, what we would like to do is to find a way, first of all, to solve the problem, and so which means we need to find all the coefficients A, B, C, D, etc. Oh, sorry. And in particular, what we would like to do is to find the relation between the coefficients in region 1, so A and B, and the coefficients in region 3, which would be F. Oh, please note that here in what we are doing, because we would like here to understand tunneling, we are assuming that our particle moves from the left toward the barrier and propagates eventually into region 3. So that's why we are already imposing that one of the coefficients in region 3 is actually 0. We should remind that the imaginary exponentials correspond to forward propagating waves or backward propagating waves. So, for example, the term corresponding to coefficient A corresponds to a wave propagating in this direction, while the term corresponding to the coefficient B propagates in this other direction, and so on and so forth. So in region 3 we need to keep only the term corresponding to the coefficient F, which is propagating in this direction, while the term propagating in the other direction must be 0, because there is no returning backward wave. So this was the first step of this process. So the second step is to introduce the so-called transfer matrix method. This is really the key of the entire method I was planning to show you here. And so the aim here is effectively to transform our problem into a problem that can be automated with the use of a computer. And so basically what we will see now is that our problem can become a matrix problem. And so this is done effectively here by imposing now the continuity and the derivability of the wave function at the boundaries of the three regions we've identified. So for example, at x equals 0, by imposing continuity, we have this relation here between the coefficients of the wave functions. By imposing the derivability of the wave functions, we have this condition. Now this is a system of two equations in A, B, C, and D that can be rewritten very cleverly in this form, in this matrix form here. So we have this matrix time a vector AB equal to this matrix here time a vector CD. And so we can write this in this form here. We name the first matrix M and the second matrix N. So we obtain this matrix equation here that we can solve toward the vector AB in this way. So m minus 1, the inverse of m, time n, CD. And so if we name the vector containing the coefficients AB, because these are related to the wave function of region 1, we name this vector phi1, the vector of the coefficients, if you like. Then we can simply write that phi1 is equal to d12, where d12 is actually this matrix here, m to the minus 1 time n, d12 times phi2, where phi2 is the vector of the coefficients in region 2, which is effectively CD. So this is true for x equals 0, and then we can do the same at x equal a, and we obtain this equation here at x equal a. Note that the symbol prime here is very important, because it is there to remind us that when we are at x equal a, there are some exponentials into the wave functions that need to be taken into account. You see, when you put x equal a in the wave function, for example, of region 2, if we go back, you will end up on this term, for example, with c times e to the I k to a. Now this is obviously a constant, but is an imaginary number that we need to take into account. So it's not just phi2 in this case is not just related to the coefficients, but there is also an imaginary number next to it, and that's why we have this prime there, to remind ourselves about that. And so this will be equal to d23, but I've put d21 because we said the region 3 is equal to region 1, okay? And phi3 prime. Okay, and just to remember, to clarify this point about the presence of this prime here, and to understand it better, we can have a look at these formulas down here. So phi2 prime is effectively this here. So you can see it's not just c or d, but is c time an imaginary number, or some exponential anyway, constant. And so if we wanted to extract from this phi2, which is obviously the vector of the coefficient CD, then we could write it simply as P2, a matrix P2 times phi2 prime, where P2 has to be this matrix here, and phi2 prime is what we just mentioned above there. So it's only if P2 has this form here that P2 times phi2 prime gives us exactly the vector of the coefficient phi2, CD. Okay, so we are effectively now defining or introducing these matrices here, P2, and P2 is effectively the so-called translation operator for our wave functions. And then we can do the same then for phi3, for example. Phi3 will be P1 phi3 prime, where P1 is effectively this And if we want to do the reverse operation, then you have that phi3 prime is p1 to minus 1 phi3. So using all these, we can now find the relation between phi1 and phi3. So the matrix of the vector of coefficients AB and the vector of coefficients in region 3, that is simply F. So for example, we've said that we obtained the result that phi1 is D21, sorry, it's D12 phi2. Or let me just note here that the relevance of these indexes 1 and 2 is that we put them in this order just to remind ourselves that this D matrix is the one that allows us to go from 1 to 2, region 1 to region 2. Now we want, because we have the relation between phi2 prime and phi3 prime, then we need to transform phi2 in phi2 prime. So we use the P matrices to do that. And so this here would be P2 phi2 prime. And now we know that phi2 prime is D21 phi3 prime. And so we replace that and now we know that phi3 prime can be translated into the phi3 vector using again a P matrix. And so we do this again here. This is D12 P2 D21 P1 to the minus 1 phi3. And so if we code, these are obviously, this is a product of 4 matrices that we can call matrix T. And so we effectively demonstrated now that we can go from phi1, which is AB, the vector of coefficients in region 1, which is effectively T, where the matrix T is obviously a matrix that has 4 elements, T11, T12, T21, T22. And so going back for a moment to our original problem, so here we said that our particle is coming from region 1. So the incoming particle is represented by the wave with coefficient A. It can be at the barrier, this can be reflected, and that's why there is the coefficient B there. But the incoming particle is the one represented by coefficient A. That's why, at this point then, if we wanted to calculate the tunneling probability, we should take into consideration and look at which is exactly the relation between A and F. So F is the wave that is emerging from the barrier and moving toward the right of the barrier. The incoming particle is represented by coefficient A. So we need to find the relation between A and F. If we do that, this will allow us to calculate the tunneling probability. And that's what exactly we do here, basically. So as you can see here, is exactly the result we just came across. T is called the transfer matrix, and it is effectively the first element, T11, of the transfer matrix, the one that relates A and F. If you go back to our result here, so if you multiply T with this vector, you can see that this becomes T11F, and the second element is T. So A is equal to T11F. Now, if we want to calculate the tunneling probability, we should remind ourselves that in quantum mechanics, probability is related to the squared absolute value of the wave function. So, because the incoming particle is the one related to the part of the wave function that has coefficient A, while the outgoing, if you like, wave function is the one related to the coefficient, the part of the wave function with the coefficient F. So in practice, the tunneling probability is effectively the ratio between the absolute value squared of the part of the wave function with the coefficient F and the part of the wave function with coefficient A, which turns out to be just this value, 1 over the absolute value squared of T11. So using this matrix approach, we can automate the calculation of the tunneling probability for any given value of the energy of the incoming particle. Now, if we wanted to solve the problem analytically, in this specific case of a finite square potential barrier, we could come up with an analytical solution that is represented in this set of equations here. So the top one is when E is bigger than V0, and the bottom one is for E smaller than V0. Or remember that E is positive, and also V0 is positive in this approach. So how much is the tunneling probability then? Well, we can have a quick look at this thing through this diagram here, where we are plotting on the abscissa E over V0. So when this quantity takes the value of 1, we are effectively at the top of the barrier, and here we have the tunneling probability, which goes obviously from 0 to 1. So classically, when the energy of the particle is below V0, so between 0 and 1, we expect tunneling probability 0, while the tunneling probability will be jump to 1 when the energy is just above the barrier. Classically, that's what would happen if we were to deal with a classical particle. Quantum mechanical, though, this is not true. Because as we can see, even when the energy is slightly below the barrier, we do have some measurable tunneling probability that is not 0. And funnily enough, even when we are above the barrier, the tunneling probability is not 1. But has this wavy behavior. Okay, we will see more examples about this in a moment. Now, to simplify a little bit further the calculation of the tunneling probability from these analytical solutions here, we can assume some simplifying conditions. For example, if K1, sorry, there is a typo here. This is K1A much bigger than 1. So if K1A is much bigger than 1, which means weak tunneling approximation, and also we assume that V0 minus E is much bigger than E, then we can demonstrate that the tunneling probability takes effectively this form. Or let me just note here that this condition simply means that if this is our barrier, and this is the 0 of the energy, and this is V0, and this is, let's say, the energy of the incoming particle, is simply saying that V0 minus E, which is this one, is much bigger than this one. So in other words, we are also saying that effectively V0 has to be much bigger than the energy. So under these conditions, we said that the tunneling probability takes this simplified form. And the most important thing to note here is that the tunneling probability is exponentially dependent from the tunneling distance. Let me remind you that K1 is simply the square root of 2m e over h bar squared. The formulas we've just seen are particularly useful and powerful to calculate the tunneling probability through a perfectly square potential barrier. The question though is, what do we do when the potential barrier is not square? There are many situations where obviously this can be the case, and the most important one I would say that we are really interested in is the one that arises when we apply a voltage across a device. Toward this end, and in order to understand why I'm saying this, we could consider the device shown here, where we have effectively an insulator, silicon dioxide, between two metals, an aluminum contact on the left and an aluminum contact on the right. The aluminum contact on the left is what we call the gate, and for example the one on the right is one that we call, for example, the source. So when there is no bias applied across this structure, the band diagram, the energy diagram of this system is the one that is shown here, where we have the Fermi level of the aluminum electrode on the left, the gate electrode, then we have conduction band and valence band of the insulator, the silicon dioxide insulating material. And then we have again the Fermi level of the right electrode that we've called the source. When there is no bias applied through the structure, we will see several times through this course that the fundamental rule is that the Fermi level through my structure has to be the same. So that's why I've drawn here the band diagram in this way. So this band diagram is the one we have to consider when we when the potential across the structure is V equals 0. Now, when we apply a potential difference between the two electrodes of this device, what happens is shown in this band energy diagram here. So what we see effectively is that if we imagine to apply the positive end of a battery to the right-hand side electrode and the negative side of the battery to the left-hand side electrode, then what happens effectively is that the potential of the energy of the right-hand side electrode effectively is pulled down by an amount minus QV, where V is the potential difference of the battery. While we could imagine that the right-hand side stays there. So this is happening because one way to see it is that the battery is providing the electrodes on the right-hand side of the energy with the energy minus QV, and so that's why the system, the energy of the right-hand side is moving in that direction. Another way of equivalent, of course, of imagining what is happening is to take a look at what really the battery does. So if we consider our device here, so this is our aluminum electrode, our piece of silicon dioxide, and our right electrode. When we apply the battery across with this polarity, what effectively the battery is doing is sending some positive charge to this end of the device. And correspondingly, if you like, sending some negative charge to the other end of the device. Or equivalently, if we think just in terms of electrons, we could say that the battery is effectively pulling away some electrons from the right-hand side of the device and is sending them on the other end. So if we think at it in this way, we could understand what is happening in our energy diagram by considering the charge that is being moved around. So if we go back to our band diagram, where here we have we draw the band diagram for a moment in the case where the potential was 0. So in presence of the battery, we said what we are doing is we are effectively removing electrons from this end. So we are effectively emptying, if this was the Fermi level, we are now emptying energy levels on the right-hand side. This obviously brings the Fermi level down. On the other hand, if you like, we are placing electrons into these empty states, and so this in effect brings the Fermi level up. So on the right hand side, the removing electrons effectively means that we are charging positively the right hand side of my device, while by placing electrons on the left hand side, effectively we are charging negatively, if you like, the left hand side of this device. And so we realize in this way that the effect of having a voltage difference across this structure is effectively the one that we have depicted there, where we have now a situation like this, where some states have been emptied on the right hand side, and we could imagine that some states have been filled on the left hand side, and so there is now this sloped energy diagram of our device. And here we have a positive charge, and here we have a negative charge. So we can further generalize this result by saying that if we place positive charges on any point of an energy diagram, this would cause that part of the energy diagram to move toward down. While if correspondingly we place somewhere some negative charge, this would cause the energy diagram to move upward. So in case we have a positive voltage applied across our device, we said we get this energy diagram, but also now we are able to understand why in the silicon dioxide region I've drawn the energy diagram in this way. If we have a positive charge here and a negative charge here, this means that on the two ends of my silicon dioxide layer, I have now charges accumulated. Positive on one end, negative on the other. And this means that there is now an electric field that is directed in this way. Oh, remember that the electric field, using electrostatic results, is given by this derivative. Remember that this is x and this is the energy. So the slope that I've drawn here is something that is proportional to the electric field. And the direction of the slope also is telling us the direction of the electric field. That is the one that I've drawn there. So all these concepts are concepts that we will come across again and are going to be very, very useful to us to understand devices operation when we start from their energy diagram. If we want to go into a bit more details regarding the potential across the device and the electric field, when the voltage is zero, the potential across the device is obviously flat and is zero and is obviously here. When we and the electric field is as well zero, and as we see is depicted here. When we do apply our positive voltage, obviously the right hand side acquires a potential V, and the left hand side stays at zero, and so there is a gradient of potential across the silicon dioxide layer as shown in this graph. And correspondingly, using the formula we just seen, E equal minus the V over dx, we can calculate the electric field through the device, and obviously the electric field is zero in the electrode areas because they are metals, and so the electric field within a metal must be zero, but is non-zero within the silicon dioxide as we anticipated previously, and is obviously also negative because, as we've seen in our previous slide, here the direction of the direction of the electric field is against the direction of the x-axis. So the electric field is indeed negative in this case. So this is to tell us that even if we know how to calculate the tunneling probability through square potential barriers, in reality what we are really interested is to be able to calculate tunneling probabilities through any potential barrier, especially because we now know that whenever we apply a potential across a device, the potential barrier seen by electrons will not anymore be square. Just to add another drawing to our collection here, what I'm saying is basically if we draw just the Venn diagram of our device, that was this one here, when the voltage was zero. So when we apply now a voltage, the energy diagram becomes, for example, something like that. For the discussion regarding electrons, it's enough to draw only the top part of our Venn diagram, energy diagram. And so we see that now one electron here will not see anymore our square potential barrier as it was initially when there was no voltage, but now we'll see something that is trapezoidal, for example. And so that's why we are really interested in to understand how we calculate the tunneling probabilities in the most general case, when the shape of the tunneling barrier, the potential barrier, is arbitrary. And this is exactly what we will do in the next slide, where we will have a look at how we do this type of calculations. The procedure that I'm going to present you here will allow us to calculate quantum mechanical tunneling probabilities through arbitrary potential barriers. What we do is extremely simple. When you have an arbitrary potential barrier, for example, the one shown here, obtained by applying some voltage across a square barrier, what you do is you divide this arbitrary potential barrier into n square barriers, and then you solve one by one the problem of the single square barrier, and then you can calculate the total tunneling probability as a superposition, if you like, of these n problems. So effectively you can relate the wave function of the particle in region 1 to the wave function of the particle in region 3 by using a product of tunneling matrices, of transfer matrices, n times in this case. Obviously, because this is an approximation, we should expect that the larger the number of slices, the better the approximation. Indeed, what we do in order to achieve a certain precision and accuracy in the tunneling probabilities we can calculate with this technique, what we do is that we need to seek convergence in this decomposition process we're doing. And this is done basically by plotting for any given number of slices we do of our arbitrary barrier, we plot the corresponding tunneling probability. So for example, here we've made here these are 20 slices, we get this value of the tunneling probability. For 40 slices we get this value here. For 80 slices we get this value, and so on and so forth. And we see that if we keep increasing the number of slices, the values tend to converge to a specific value. So it's then the accuracy we require that will decide at which number of slices we have to stop this process. And so using this numerical technique, we can effectively calculate for any given energy of the particle that is impinging on the arbitrary potential barrier, we can calculate the corresponding tunneling probability. So we can effectively, for this value of energy, calculate the corresponding tunneling probability. So imagine now to repeat this process for a different value of the energy of the impinging particle. So we will be able, through this technique, to calculate another point on this plot. And in the end, we can effectively construct this function, the function that gives the tunneling probability for any energy of the impinging particle on the potential barrier. Now, this is particularly important because using this function we can now calculate through this very horrible looking formula the tunneling current for that specific bias or electric field that we have applied across our barrier. So this will give us a point on this plot where we have the electric field applied across the device and the corresponding tunneling current. So it is, you can see this formula requires the function TE, the tunneling probability. The reason why this formula is this shape is explained in this paper here, where the entire derivation has been made. And so by applying now a different value of the voltage and repeating the entire process, we can then calculate another value of the tunneling current for a different value of, obviously, of the electric field, and so on and so forth. And so we can use this process again and again to effectively calculate the tunneling probability, the tunneling current of charge carrier through my potential barrier for any value of the electric field. In this slide, I'm going to show you some results of this process I've just explained to you. It's a very powerful technique, and I will show you here some examples applied to silicon dioxide. So the device we are taking into consideration here is again a device made of an aluminum contact, silicon dioxide, and then a p-silicon substrate. P-silicon is heavily doped here, so it effectively behaves as a metal, and we will look at it as it is, as if it is a metal. So here the metal, the aluminum metal is on this side. As you can see, the gate, we call it the gate. Then we have the silicon dioxide in between. In this case was 3 nanometer thick, and then we have the side where the silicon is, and the barrier height here, where is this red square, is actually 3 eV. Okay, so using our technique, the transfer matrix method technique to calculate tunneling currents, we can first of all calculate, for example, tunneling probabilities for any given energy of the particle. Here we imagine that, as you can see, we are imagining that the particle is coming, for example, this way. The electron, sorry, is coming this way. So the barrier is 3V, and so we can see here two curves. The black one is for a device that has no bias across the device, and the pink one is when we apply an electric field of 10 megavolt per centimeter, and we can see that obviously when we apply a large bias, and so we are effectively in this situation here. So the pink curve is effectively related to this band diagram. The tunneling probability increases even a lot in the forbidden region, in the region that is between 0 and 3 eV, which correspond to the barrier. The dramatic changes that are happening to the tunneling probability function are actually seen better in this plot here, where we plot the tunneling probability in a log scale. So as you can see, for no bias across the device, we have the black curve here. As we increase the bias applied, the electric field, we move to the pink curve here. So as you can see, there are many orders of magnitude difference between the black curve and the pink one. It is though interesting to note that even with no bias applied across the device, the tunneling probability in the forbidden region is never 0. And this is exactly what we tried to emphasize a few slides ago by explaining the differences between the classical case and the quantum mechanical case. So there is always a tiny small probability that electrons can tunnel through the barrier, even at 0 bias. So now, using these tunnel probability functions at different biases, we can calculate the tunneling current versus the different electric fields. And so for the case of 3 nanometer silicon dioxide, we get the black curve here for positive electric fields and the negative electric fields. So as you can see, as I said, this curve is for the case of 3 nanometer silicon dioxide, as the one that was depicted in the band diagrams here. We can see that the curve is made of two parts. The first one that is indicated by this arrow that we marked as the T regime, and the second part that is now not clear, not visible, but is the one that is actually going like that here, that is marked as FN regime. Now this is pointing us to two types of tunneling regimes. The one is called direct tunneling, DT regime, and the second one is called FN regime, Fuller-Nordheim, and they simply refer to the fact that direct tunneling is the tunneling that takes place through a square or a trapezoidal barrier. Fuller-Nordheim tunneling is when tunneling is through actually a triangular barrier. So we can understand why this tunneling current curve is made of two branches, if you like, by simply looking at the band diagram. So when the voltage across the device is small, the bending of the band diagram is also quite small, and so effectively the electrons tunnel through a square or a trapezoidal barrier. If we increase further the voltage across the device, the potential barrier becomes effectively triangular. At least it is seen as triangular by the tunneling electrons. And that's why we have a first part that is dominated by the direct tunneling regime, and a second part at higher electric field that is dominated by the Fuller-Nordheim regime. So on this plot I've also done now the same exact thing for silicon dioxide layers that are thicker, so 4 nanometer, 5 nanometer in green, 6 nanometer in blue, etc., etc. So as you can see, the Fuller-Nordheim plot seems to be universal, while the direct tunnel regime is actually different, at least in values. And this is a nice feature that you should note. Let us consider now another interesting case of related to tunneling, and this is the so-called resonant tunneling. Now, in order to analyze this case, we have to consider band diagrams that look like the one that I've shown, the one that I've drawn here. The band diagram is effectively made of two barriers with a finite, effectively, well in between. In this specific case, I'm assuming that all parts have a thickness of 1 nanometer, so the first barrier is 1 nanometer thick, the well is also 1 nanometer thick, and the second barrier is also 1 nanometer thick. And the height of the barrier is 3 electron volts. So in this case, if you use our transfer matrix method to automate the calculation of the tunneling probability function as a function of the energy of the impinging electron, then you realize that you get the results shown here with the black curve. As we can see, in the forbidden region that goes from 0 to 3, where the barrier is, the tunneling probability is particularly high. Not only that, but in some specific situations, the tunneling probability becomes effectively 1. For comparison, in the case of no well between point 1 and 2, the tunneling probability would have been the one presented in with the dashed line, so much smaller as well, and obviously with no spikes if you like. So this is a very, very interesting phenomenon here that goes effectively under the name of resonant tunneling. And the reason is that it goes under this name is that effectively for these energies here, the electrons that are impinging on this barrier, on this structure, with these energies effectively go through without seeing the barrier, because the tunneling probability is effectively 1. So how can we interpret this phenomenon? Well, the one way of interpreting this is to say that at those 3 energies that we've seen in the previous slide, that are basically around 0.25 eV, 1 eV, and 2.2 eV, we could say that there are some quasi-bound states effectively in the well that aid the transmission of electrons at that energy level. If we now imagine to apply some voltage across this structure, what will happen is that, as we anticipated in a previous slide, the band diagram will actually change, will be slightly modified by the application of this voltage across the device. So if we imagine that the band diagram we are dealing with here is effectively made by a metal, and then this region here is made by a semiconductor, and then another metal, and so on and so forth, another semiconductor and another metal. Then when we apply a voltage across this structure, we know that the potential across the potential across metal has to be the same. So the regions where there is a metal, they have to stay flat. They cannot bend under the influence of a potential change. So all potential changes have to go through either the region where there is a semiconducting material or an insulator. So that's why here here we have applied this voltage across the device. So this potential change is only going to affect the bending here and here of the semiconductor sides. But what is now really interesting to note here is that by applying a voltage across this structure, we are effectively moving up and down these quasi-bound states. And so we should expect that when these states align with the energy of the impinging electrons, those electrons will tunnel through the structure and move to the other end. So we will have a high current, basically, in that case. Now, if this level here represents the Fermi level of the metal, well, most of the available electrons will be around these energies here. Okay, so this means that anytime a level is aligned effectively with this energy, here the electrons travel through the structure. And so in other words, what in the end will happen is that if we were to look, or we were interested to look at what the current density through the device looks like as a function of the electric field, then we should expect a graph like this one here, with spikes that correspond to electric field E1, E2, E3, that make each state align with the structure. Just to make this a bit clearer, we can look at this a bit more in detail. So when we have our structure here with no bias across, we are in this situation, and say that we have this state, and this state. So an electron in this position, that is an electron in this position cannot really tunnel easily through, because there is a mismatch between its energy and the first available level here, quasi-bound state. So if we now apply a slight voltage, a small voltage across the device, at a certain point level 1 will align, and so the electron that is here will now happily tunnel through the entire device. If we increase a little bit more the voltage across the device, we are now in an intermediate situation where this electron could obviously tunnel by doing something like that, but obviously this is not so favorable as before. But if we keep then increasing the voltage across the device, then at a certain point we will align the second state with the energy of the incoming electron. And so we are in this situation where again the electron will tunnel through. And so this is the reason why we should expect the tunneling current through the device as a function of the electric field to have this form, with spikes at certain specific electric fields that induce the alignment of the quasi-bound states with the tunneling electrode, the electrode from which tunneling is taking place. Okay, at this point, for the resonant tunneling case, a question comes to mind, which is, can we predict where and how many are these resonances? Well, the question is, to some extent, yes. And the way we do this is we use the results we've got from the finite quantum well as a zero-order approximation, basically. So, referring to our example that we've had a look at previously, which was basically this one here, where, for example, we had we've used in our calculations a mass of the electron equal to m0, the well is 1 nanometer, and the barrier is 3V. So if we use now these results and apply them to the case of the finite quantum well results, then we can easily establish that V0 over EL is 8. EL, if we calculate it in our case, L is 1 nanometer in our case, so we can calculate EL is 0.37. So remember, we are trying to apply the finite quantum well result to this structure. Okay, remember that the finite quantum well is actually this situation here. Okay. So let's go. Let us use now again the graph that we identified previously, which allows the graphical solution of the eigenvalue problem for this for the finite quantum well case. So if we imagine here to draw the red curve for V0 equal 8L, we would easily realize that this curve has to be somewhere in between the 5L case and the 10L case, and hence has to end up here at 8. So we can easily realize that we have to expect an eigenvalue here, an eigenvalue here, and an eigenvalue here. So this approach is telling us that we should expect 3 eigenstates, 3 eigenvalues. And if we, so 3 bound states, which is exactly what also our tunneling probability simulations said, and we need to expect the first state as 0.7 EL, 2.6 times EL, and a 5.3 EL. If we translate those numbers in EV, then we have that our finite well approximation is actually estimating or predicting the first bound state as 0.26 eV, the second as 0.96, and a 2 eV. As you can see from comparing the results we've got from simulating the tunneling probabilities through the structure, the resonant tunneling structure, with the prediction using our approximation based on the finite well results, the match is absolutely amazing, I would say. So the finite well is a very nice tool to use in order to estimate the number of bound states in the resonant tunneling device, and also get a quantitative estimation of the energy level of those bound states. In the previous slides, we have had the chance to realize how important is quantum mechanics when it comes to nanoscale materials and structures. We've seen, for example, that while in a bulk material we would never think that a particle, an electron, can move through a barrier. Suddenly in the nanoscale there is a finite probability that an electron can tunnel through an energy barrier. So in order to continue the exploration of the effects, the quantum mechanical effects that take place when we go into the nanoscale, we will discuss here what we call quantum confinement. This concept is obviously related to things that we've already in a way mentioned in the previous slides. And to put it in simple terms, quantum confinement refers to the effects that shrinking the size of a material, either one dimension or more than one dimension, has on their physical properties. The fundamental result that we would like to discuss here is that these effects on the physical properties of materials arise because of the discretization of the energy levels in those materials where we have reduced the size either in one dimension or in more than one dimension. In order to understand what happens exactly to the energy level, to the energy levels of materials when we shrink one or more of their dimensions, we should first of all remind ourselves that we are using here Fermi-Dirac statistics, as we are dealing with fermions, electrons, and so we have to definitely rely on the Fermi function, which we have already seen previously in our slides. Remember that the Fermi function tells probability to find an electron at an energy E when the system has a Fermi energy μ. Now, in our material, if we wanted to calculate generally the total density of electrons n, what we should do is this integral here, where f is the Fermi function and g is a distribution function that tells us how many states are available at that given energy E. And this function is a very important function, and it is called the density of states. This density of state function, GE, is related to the number of states available up to a certain energy through this very simple derivative. Sorry, here there is a missing letter. This is D and S. So here there is an S. To remind us that this n here is not the n that we've put here for the density of electrons. This is the number of states. Okay, that you can see also down here. So the number of states available up to a certain energy F can be calculated in this way. So we integrate from minus infinite to EF the density of state function. And this integral returns the total number of states available up to that point. So it's actually through this relation that we will now attempt to calculate the density of states in several different situations for materials of different dimensionality, to explore exactly what we said previously, what happens to the energy levels of our materials when we shrink one or more of their dimensions. In order to do this, we use a two-step process. The first step is to calculate the relation between E and K in our material. The second step is then to, through basically this, having in mind this relation here, what we do is we first find the relation between the total number of states and K, and then we replace K with E. We do this change of variable. Once we do that, we have an expression that relates the number of states and S and E. So it's through this relation, and then we will try to find G. So that's the approach that we will follow, and we will explore in the next few slides what happens in the 3D case, 2D, and 1D. So initially we will first demonstrate maybe which is the EK relation for the three cases I've just mentioned, and then we will use these relations to then go on and calculate G for all these three cases. So let us start with calculating the dispersion relation in 3D structures. Oh, let me, I forgot to mention that the EK relation, although we've mentioned this probably previously, the relation EK between the energy and the wave vector K is called the dispersion relation. Okay, so let us try to find the EK relation for a 3D structure, a bulk material, a macroscopic piece of material. So what we do in this case is we obviously the material is macroscopic, so all the electrons can be very well modeled by plane waves, and so they are basically can be treated as free particles, and so we know that the energy in this case is related to K in this way. So this would be true if we are in one dimension, but we said we want to treat the 3D case. So in this case, K is actually a vector, and so Psi is also a vector, and so we need to write the 3D Schrödinger equation ideally, which we can do here in this way extremely simply. Because we said we are in the case of a macroscopic piece of material, we should assume that we are in absence of any external forces, and so we can, for the sake of this discussion, assume that any potential is zero, and so effectively along any direction the system can be treated as a free system, and so the total energy is simply given by the sum of these three terms, one relating to x, one related to y, one relating to z. So effectively the energy in this case is a parabolic function of k, kx, ky, and kz in all three directions. So this is effectively the relation, the EK relation for the case of a 3D structure. If we wanted to visualize a little bit better these things, we should remind that obviously if consider just one direction, one dimension kz, we are talking of a parabolic relationship between E and kz. Obviously the same holds also for y and also for x. Okay, so in an attempt to try and see this relation in a three-dimensional space, obviously it's not possible because we have effectively four variables here, kx, ky, kz, and e to plot, which is not possible. What we can do though is to assume for a moment that kz is 0, and let us plot the remaining part of the relation ek. So if we plot that, this would look like, if you assume this is x, this is y, and this is e, sorry, this is kx, and ky? Well, the dispersion relation is actually a paraboloid. So all the states allowed to this system are the points that sit on this surface. Oh, remember that kx and ky can take any value, are real numbers. So effectively, any point on the surface of this paraboloid is an accessible state to my system. If we drop the assumption that kz is 0, then effectively the relation between kx and ky, which was, I remember, is plus a certain constant c, where this constant c is the term concerning kz. Okay, so if we allow now, if we drop the assumption that kz was 0, which we assumed simply to be able to draw this paraboloid and to understand what type of shape we are dealing with. So if we now drop the unreasonable assumption that kz is 0, kz can be any value from minus infinite to plus infinite, we are dealing with plane waves. This means effectively that we are adding to our paraboloid function a constant, positive, because h bar squared, kz squared over 2m is a positive number, whichever value kz takes. So this means effectively that by letting kz vary in its range, any point within the volume of this paraboloid, within this surface, is effectively a state that is accessible to my system. So any point within that volume effectively represents a suitable state for our system. Okay, this slide basically reminds you exactly what I was trying to tell you previously. So remember that the dispersion relation we've just seen, the wave vector either is x, y, or z, is basically any real number, means that any point on the EK dispersion curve is suitable state for the system, and so there is a continuum of states. This parabolic shape of the EK relation, so when EK takes this form, is particularly important in general because we use this parabolic shape to actually approximate the real band structure, band diagrams of real materials, at least locally. So for example, if we take this part of the band diagram of this germanium, we could locally approximate the real energy wave vector relation with something like this. Let us consider now the case of a 2D structure. So in a 2D structure, what we are doing is that x and y, for example, are macroscopic, while we are shrinking the dimension z. This situation is called also that of a quantum well. In this situation, the electrons are free to move in x and y, but they are confined in z. So here we starting now to introduce confinement into our structure, and let us see now what will be the consequences of that. So for simplicity, we will work under the following assumptions: that the potential is separable, so that V, which is in general a function of x, y, and z, can actually be separated into three components, three parts, each of which is in a different direction. So Vx for the direction x, Vy for the direction y, and Vz for the direction z. And again, we assume that we are in equilibrium and that there are no external forces acting. So we assume that along the direction x, the potential is zero. Along the direction y, the potential is zero. But along the direction z, because of the finite size of our material in the direction z, we have to assume conditions that are the same of the ones that we encountered with the infinite potential well in quantum mechanics. So this function here that has been defined using an arbitrary potential V0, a positive number V0, and the step functions are actually there to create something that reminds us the potential well, and then if we push V0 to infinite, we are basically recreating the infinite potential well. So if we wanted to clarify these definitions and see them better on paper, we could do the following thing. So reminding that x, y, and z. So remember that z is the dimension that we have confined. So if we were to plot the potential along x, this is the energy, so the potential along x, would look like that, is zero, all the way. If we were to plot the potential along y, this also would be zero. If we were to plot instead the potential along the direction z, now depending where we put the origin of z, but we could assume that it's in the middle of the material, for example, and so this is V0. And we then push V0 to plus infinity, and so we create the infinite potential well. This would be minus L over 2, and this, for example, L over 2. And this is the distance L that is actually the size of our material, at least that we've confined. Yeah, so this is LZ. So since we are working under the assumption that the potential is separable, so the Schrödinger equation can be separated, a problem for the x direction, one problem for the y direction, and one problem for the z direction. So in x and y, because the potential is zero, the problem is solved simply by using as wave function plane waves, and the eigenvalues are those that we've seen previously. So as we can see here, psi and psix are given by these terms here. Now, and the corresponding energies are the terms corresponding to these plane waves in the eigenvalues are these two here. On the z direction, though, because of the confinement and because we said that we are basically dealing with an infinite potential well, we know how to solve the infinite potential well, so we know that along z the solution has to, the wave function has to look something like that, and that the energy level are discrete now, and the energy level are identified through the quantum number n that goes from 1 to infinite. So this is the EK, excuse me. So this is the EK relation into D. And as we can see, Kz has disappeared because it's now quantized and has been replaced by our quantum number n. If we wanted to plot this relation, we could do so, for example, assuming n equal 1. So the quantized term here would be a constant, and so this means that we would draw a paraboloid, because E is a function of two real variables kx and ky, and we know already that this gives us a paraboloid. If we then change n, this number, this quantity becomes bigger, so the constant we need to add to this paraboloid is bigger. So basically we are shifting the paraboloid upward. So there is another paraboloid just above the previous one, that is this one here, and so on and so forth. So we can see that the discretization of the energy levels causes here the appearance, if you like, of paraboloids that are separated by a finite energy. And that finite energy is the separation between the discrete levels of the infinite potential well. One thing that probably I didn't stress too much is how we get this result here, that in a separable problem psi xyz can be written like that. So let me just spend a moment to explain that. So if this is our Hamiltonian and this is our wave function, so this is our Schrödinger equation, eigenvalue equation, and we know that H is so if V, as we said, can be written as Vx plus Vy plus Vz, and this is just a function of x, this is only a function of y, and this is only a function of z, then our Schrödinger equation can be written in this way. So this would be H, and here we need psi equal, run out of space, sorry, ipsi. So, but here now what we realize is that we have one problem in X, just X, one problem in Y, and one problem in Z. So this means that our psi X, Y, Z, which in general is a function of these three variables, if we split it in excuse me, in this way, then the problem in X applies only to this component of the our wave function, the part in X, because it's the only one that depends on X. The problem in epsilon applies only to this one here, and the problem in Z applies only to this part here. Remember that the reason I'm saying this is that the operator derivative in X will apply to psi X, which is a function of X, but it will not apply to the remaining functions because they are not functions of X. So, and the same applies for the same argument can be used for d dy or d dz, for example. So, and it is with this argument that we can demonstrate that if this is true, then we can look for solutions to this problem of this type. Okay, let us discuss now the case of the dispersal relation in 1D structures. So in this case, one dimension is infinite, while the other two have been confined. So electrons are free to move, for example, in Z, but they are confined in X and Y, as shown in this diagram, in this image here. So in this case, similarly to what we've done with the 2D structure, our potential, we assume still that it is separable. And so in this case, we have a potential well in X direction and a potential well in the Y direction. That's what this expression here is basically doing. So in this condition, again, using similar arguments that we used also in the 2D case, it is the wave function in the Z direction is that of a plane wave, which means that in the Z direction, the term in the eigenvalues is given by this term here. On the other hand, in E along X and Y, we are dealing with infinite potential wells, and so the wave function has the sinusoid solution that we mentioned previously, and the eigenvalues are quantized now and are given by this function here. So in this case, both kx and the ky have disappeared from the energy of the system and have been replaced by two new quantum numbers, nx and ny. Both go from 1 and to plus infinite. And so this is the formula that provides the total energy of our system as a function of k, z, and the two quantum numbers. So if we were to plot this EK relation as a function of kz, of the only real variable in this relation, we know that this function is actually a parabola, and so for any given value of an x and an y, this term here is a constant added to a parabola that would otherwise go through the zero. And so, but remember that an x and an y can't be zero. So this means that this constant here is always different from zero and positive. So this means that we have, for an x and an y equal to 1, we have this first parabola here. And then as we increase either an x or an y, the successive parabola will be slightly shifted upward, and then more, and so on and so forth. And so we have, as we did in 2D case, different modes where our states are allocated. So as we did in the 2D case, let me just clarify some things on paper. So we have our x was going like that, x, y, and z. So x and y are quantized, and z is infinite, our material. And so if we were to plot, also in this case, the energy of our system along, for example, along x, this would be, as we said, potential well. If we do along y, we said that also we are in a situation where we have potential well because the system has been confined. And finally, along z, the potential is zero because the system is infinite and the electrons can move freely. And remember that V0 tends to plus infinity, so this is going up, and we created the infinite potential barrier this way. Remember that this is minus L over 2, minus Lx maybe, Lx over 2, and so this is Lx, for example. This is minus Ly over 2, Ly over 2, so this is Ly. Just in the case that obviously Lx and Ly are different from each other. So if we wanted to understand a bit more in detail the EK relation in this case, so the EK relation in this case that we should remember is plus the term corresponding to the plane wave where Nx and the y go from 1 to etc. So we should probably, to understand very well this how this formula works, do some calculations here and see what happens. Let us, for simplicity, assume that Lx, excuse me, and Ly are the same. So this basically means that E is proportional to something that contains nx squared plus ny squared plus something that is in kz, okay, kz squared. Obviously there are some constants here in front. We are not interested in the constants right now. We want just to understand the trend here. So let us, for the sake of the discussion, assume that all the constants, the other constants involved are 1. We want just to understand what happens to the lowest point of the parabola, basically. So remember that we just said that the EK relation in this case is going to generate a diagram that would look like this. So when Kz is 0, the energy is here on the different parabolas. So this is the energy we want to consider. So let us consider, okay, and let us assume that all the constants that are involved in this formula, h bar, pi, are 1. So we don't have to deal with these details, but we want to understand the trend. So we said that nx and ny can take values from 1, 2, 3, and up to plus infinite. So the lowest values we can consider is, for example, 1, 1. So if we give 1, 1, 1 squared plus 1 squared is 2. So this would be something proportional to 2. When we then give the value 1, 2 or 2, 1, one squared, for example, plus 2 squared, this would make 5 in both cases. In both cases, because we have assumed that there is some symmetry in the system. And so on. For example, we can, the next one would be 2, 2, and we would have 8. And then we have 1, 3, and 3, 1, for example. Which makes 10. And then we have 2, 3, or 3, 2, which makes 13. So we can see here not only which quantum numbers nx and ny gives what energy, but also we can see the degeneracy, if you like, of that specific combination. So we can see here that we can call this state 1, 1, this mode, if you like, 1, 1. So this is, for example, E1, 1. We can call this situation E1, 2 or E2, 1, it is the same. And this is the next mode, next band, if you like. So this would be this point here, E1, 2. So we can call this mode 1, 1. This is mode 1, 2. And this has a degeneracy of 2. Then we have E2, 2 would be the next one. So this would be E2, 2. This is the mode 2, 2. And this only, the degeneracy here is 1. There is no other state like that. And then we go E13, which would be the next one, and this has a degeneracy of 2, so we can put next to this the degeneracy of the state. Here is 2, here also is 2, and so on and so forth. One last remark goes to the wave function of this in this case. So we've said that the total wave function is the product of the three different components along x, y, and z, and while along z we said that the wave function is that of a plane wave, along x and y is a sinusoidal form. So along x and y we are expecting something along these lines. Now, because kx and ky are effectively quantized, as we said, with a quantum number nx and ny, taking those values, then it's interesting to observe how along the xy plane the probability of finding an electron looks like. Remember that the probability of finding an electron is calculated by calculating the absolute value squared of the wave function. So if we do that for this case, then we see that when we consider the mode 1-1, then the probability to find the electron is very high at the very center of our confined space. Remember that x and y are confined, our material is confined, and so in this case, for example, our material goes from 0 to 2, whatever units are here, and along y goes from 0 to 1. So our material is within these limits, has been shrink down to this level. And so in this case, the wave function has to live within this space, and the wave functions are obviously these ones here. And if we do the absolute value square of the wave function for quantum numbers 1-1, you observe that the maximum of the probability of finding an electron is actually in the middle. If we then go to more complex modes, for example 2-1 or 1-2, then you see that you have this situation here, is split in two. If you go to 2-2, the next one, you actually have 4 points where the probability of finding the electron is highest. We can understand very quickly how these graphs can be generated simply by considering the sinusoidal form of the wave function of the eigenstates in the infinite potential well. So if you remember, in the infinite potential well, we've said that in the first state, which is for quantum number 1, the wave function is something like that. For the second state, the wave function is something like that, and so on. So let us now try to export this information to our confined material in x and y. So in the case 1-1, for example, we do have a wave function along x that has to go something like this, and along y it has also to go like that. And so you understand that if you combine these two and you do the absolute value squared, the highest value of the combined function psi(x) time psi(y) will obviously be in the middle. If you then consider the case 2 1 or 1 2 is the same. So let us consider the case along x1 and along y2. So if along x the quantum number is 1, again along x the wave function looks something like that. While along y, because the quantum number is 2, has to have something like this. And so overall, the absolute value squared of the wave function should be maximum in these 2 points. And so on and so forth. Similar explanation can be considered for the case 2 2. So that we can draw here very quickly. So the case 2 2, we have along y we have this wave function, and along x as well we have this wave function. And so along x we expect that the absolute value squared is always maximum around along at this value of x and at this value of x. Along y we are expecting along this value, and so overall we are expecting 4 points where the combined wave function will be absolute value squared of the wave function is maximum. Okay, just to conclude our investigation of what happens to the EK relation once we decrease the dimensionality of our structure, let us consider the extreme case of 0D structures. So a 0D structure is effectively a quantum dot, is confined in all dimensions, and so following what we've done in the previous situations, we can expect that we have quantization in all directions, x, y, and z, and so there is no real dispersion relation here, because all kx, ky, and kz are quantized, but E is given actually from something like this formula, where kx, ky, and kz have been replaced by 3 quantum numbers now, an x, and y, and a z. And so in reality, the available states for this system are all quantized. And similarly to what we have done in the case of the 2D structure, it is useful to try to figure out which state is the lowest, for example, and which is the corresponding degeneracy of each state, and so on and so forth. And this can be done easily here by considering, potential combinations of these 3 quantum numbers, and correspondingly calculating the energy and checking how many states have the same energy, for example. So it's obvious that 111 is the lowest level available to this system. We can call this E0, and obviously there is only one state that one combination that gives this situation. So the degeneracy of this state is 1. 112 is the next available state, closest in energy, and the degeneracy in this case will be 3, because if we assume that again Lx, Ly and Lz are all the same, then whether we consider the combination 112 or 211 or 121, they will all give the same energy that we shall call E1, for example, and so on and so forth. So the same happens for the next combination 1, 2, 2. Okay, this concludes the first step of our process. We now have a clear idea of what happens to the EK relation of a material when we decrease its dimensionality. But our goal is to actually try to calculate a more important function, that is the density of states. So in order to do that, we need to actually start counting the states. And that's what we will do now in the next few slides. So we will consider again 3D structure, 2D and 1D, and for each one of these we will start counting the states and to finally calculate the corresponding density of states. So let us start with the 1D case. Even if in our previous slides for the 1D case, we've said that 2 dimensions are confined and 1 dimension is infinite. Obviously, in practice, no dimension is ever infinite. No material can be ever infinite. So even if in that dimension the material has a large size, it will always be finite. Our finite 1D structure can be something like this. Obviously, 2 dimensions are very confined, and the other one is finite. So, because in our previous analysis we assumed that 1 dimension was actually infinite, how can we re-establish this condition of 1 dimension being infinite if my piece of material is finite? So the idea here is to imagine hypothetically that we could place many of these objects next to each other, head to head, and eventually make it infinite. Now, if we do so, we need though to assume some border conditions for our wave function, because for our real object the wave function has to live within the object. So what we do is that we impose periodic boundary conditions, which means basically that my wave function has to repeat itself once we go beyond the limit of my real object. So that's the key concept with the periodic boundary conditions. So the only allowed wave functions are those that effectively beyond this point repeat themselves. Now this condition has the result that effectively Kz also is discretized. And the separation between 2 neighboring values of Kz is actually this. We can demonstrate this relatively simply by saying that under periodic boundary conditions, the allowed lambdas are given by the length of my piece of material divided by n, where n is a an integer that goes from 1 to infinite. The reason for this is that if this is my piece of material that is confined, as we said, in x and y, and this is the z dimension, and so this length is Lz, then the periodic boundary conditions impose that the first suitable wavelength, if we think for a moment just to sinusoid functions, would be this one. This is the first function that would repeat itself if we imagine to do the operation we said previously. The second one would be this one, and so on and so forth. So the wavelength of the first suitable wave is actually Lz, and all the others are obtained by dividing Lz first by 2, then by 3, and so on and so forth. So this is the initial realization, and so once we do that, we remember that k is 2 pi over lambda, and so this means that k is n times 2 pi over L. And so this is our delta k. So this means that, kz. So this means that our kz, that we thought it was a real variable, so could take infinite values, when we actually move to finite materials, it isn't anymore, but it is also quantized in a way, and this is the discretization factor. So, having realized this very important thing, we can now move on and start counting the states. Now, on these slides, I've put the fundamental results, and I've put here also the final result we are aiming for, which is the density of states for our 1D structure. But I would like to go through the actual calculation, because it tells us a lot and lets us understand a lot. So the way we can now start counting the states for our 1D structure is the following. So let us first of all remind ourselves that what we are aiming for is a function GE that we call density of states, that allows to calculate the total number of states available in our system up to a certain energy through this equation here. Now, in 1D structures, the EKZ relation is represented here with these parabolas at different shifted upward because of the different modes, but we have said that we have a certain step now between the available KZ value to the system. So KZ is also discrete. In KZ space, it is actually relatively easy to count the number of states available to the system. Just because KZ lies on a line, we know the separation between two neighboring available states. So if we know that my system can go up to a KZ that is KZ tilde here, that correspond to the total energy EF, then it's just a matter of counting this number of states. You can just divide kz tilde with the delta kz. And that's what we do here in a more fancy way, but that's exactly what I'm doing here with this integral. So let me just change color. So here we are considering, first of all, we are adding a number 2 due to spin degeneracy. We are adding this number 2 because kz obviously can take positive and negative values. And so because of the symmetry in kz, we would like to put a 2 here so that the integral can be done only on the positive values of kz. And so then there is an integral here that goes from 0 to our kz tilde of our infinitesimal movement on the kz direction, that is decay basically, divided by the step that we've already identified, the delta k z. So if we substitute, we get this expression here, and which we can fix further in this way. So by comparing what we've got with this, we could say that the quantity 2L over P, this is an integral over the K, the quantity 2L over P could be looked as our G of K, but we don't want G of K, we need a function of E. So we need to go through now a change of variables in order to do that. Oh, let me just emphasize here that in these steps I'm doing, I'm considering just one mode for now. So let's pick up one of the possible modes, let's say nx and y, to leave it general. Okay, at the end we need to then add up the results coming from all the modes. So we'll see how we do that. But let's now assume that we are considering just one of the available modes. So we said now we have got our sort of function gk, but we don't want gk, we want ge. So as a function of e. So let's see how we do that. So at this point we need to remember that in 1D structures the dispersion relation ek allows us to express k in this form. And so we need to now change variables. So within the integral we need to also change dk into dE, and we do it very simply doing this, and dk over dE is calculated from the relation we've just written up here. So we derive that and we obtain this result here, and I've missed, I think there is a D missing here and a D missing here. Okay, so anyway, we then since we are changing variable, we need also to change the extreme of integration, the extremes of our integration. So for k equals 0, the energy for k, if we look at the formula, for k equals 0, it means that the energy is E and X and Y, and for k equal our kz tilde, excuse me, I forgot, okay, kz tilde, the energy is EF, according to the diagram I've shown you previously. So we can go back to our integral and change finally variables, and so we get something like that if we put everything together. Oh, note that I've added now this function here, and the reason of this function is explained here below. when we do this square root, for this square root to be a real value, we need to require that e is bigger than e and x and y. So we need to make sure that the mode we've chosen is such that basically e and x and y is smaller than the energy e. And that's what the step function here is basically doing. If e is not bigger than e and x and y, the step function gives 0, and so the integral is 0. If instead of considering just one mode, we are dealing with many modes or many bands, then we need to consider all possible combinations of nx and ny quantum numbers. And so basically our previous integral changes in the way that I've shown here. So basically we need to add this sum, and this means that we have identified our g 1d as a function of e, which is finally this one here. So we should note here that there is a square root on the denominator, and there is also this step function here, which means that if we try to plot this function, we should end up with something like that. As you can see here, the density of states up to a certain point, this would be E11, is 0. There are no states there. Remember, the system is quantized in both x and y, and if you remember the dispersion relation, the EK plot also showed that. And so it's only when the energy or E is above the first available E and X and Y, which is E11, that we start having some states available. And the shape of the function is the one you see here with these spikes. The spikes are because of this square root, inverse square root dependence. Let us consider now the 2D case. Let us calculate the density of states in the 2D structure in the quantum well. So similarly to what we have done in the 1D case, we now know that because of our 2D structure, while it is confined along Z, it cannot be really infinite along X and Y. So it will be somehow finite also along X and along Y. And this causes the fact that we have some discretization of Kx and Ky as well. And so overall, if we take both Kx and Ky together, if we look at the K space represented by the plane Kx and Ky, this discretization corresponds to an area delta K squared that is given by 4 pi squared over A, where A is Lx times Ly, the real size of this our piece of material. So this means that on the Kx and Ky plane, the states are not continuous, but are actually discretized, and delta K squared is actually the area that represents, that quantifies the discretization taking place. So here we can visualize what we just said very nicely. and so everything becomes now, I hope, very clear what we are doing. So the only states available for this system are those represented by the blue dots. So let us now try to calculate our density of states in this case. And so we need to start counting the states, as we said. So here again, I've summarized the major results for this calculation. But again, I want to show you the details of the calculation, which we can do here. Now we understand more or less the process. So since delta K is in this case given by an area, delta K squared. So in order to count the states on the Kx and Ky plane, it's better to use polar coordinates. So what we should do is to consider a circle of radius K and one of radius K plus decay. So the area between these two circles would be this one, 2 pi K decay. So the total number of states up to a certain value K can be simply calculated by dividing this infinitesimal area by the delta K squared and integrating over K. And this is what we will see in the next slide. So the total number of states up to a certain K tilde, remember this is the radius on the Kx and Ky plane, is given by this integral here, as you can see, is 2 pk decay divided by the delta K squared we identified previously. The integral is done from 0 to K tilde. Again, we have the degeneracy for the spin. And so if we do the calculation, we simplify the terms, we quickly realize that this function here is could be our gk. Again, we need to transform this into ge. And so we recall that into this structure, the relation between E and K is this one here. So we express K in terms of E in this way for a 2D structure. And so in following really what we've done in the 1D case, we repeat the process, as you see, calculate decay, and then we calculate the extremes of integration. For K equals 0, E will be equal to En. Oh, again, I forgot to mention this, but in order to do these calculations, initially we always assume that we are dealing with one single mode that we decided is mode N, and then we will see what happens when we need to consider all the modes together. And so if we do the change of variable into our integral, we can see that the steps are done here. Again, we introduce a step function that is to ensure that the square root is a real value. And so we end up with this result here. So again, if we now consider the general case where there are many modes involved, then we need to consider adding this sum into the integral over all the modes that have an energy En below the energy. Okay, that's the meaning of this sum. And this is our density of states in 2D. So as we can see, what is remarkable in this situation is that the only dependence of this function from E comes through the step function. this creates this funny shape of our density of states. So again, this would be our E1. Again, I should remember that in the 2D structures, the dispersion relation is made of paraboloids separated in energy, if you remember. And so this would be the energy of the first mode, and this the energy of the second mode, and so on. And so it's only when the energy we are considering is just above the first available mode that we start seeing some available states for our system. And this function is flat here because, as I said before, this density of states depends from the energy only through the step function. Okay, let us consider finally the case of a 3D structure. So our structure is not confined in any direction, is though finite, cannot be infinite. So the discretization takes place in all three directions, x, y, and z. So we are dealing with a discretized volume in K-space. And again, here are the major results that I'm anticipating. Let's have a look at the calculations here. So we now understand how the process works. In this case, what we do is that in order to count the states, we need to consider the states that are in the volume existing between a sphere of radius k and one of radius k decay. And such a volume is given by this value. So in order to calculate the total number of states, we have to do this integral here. So on the numerator, you see the volume we just calculated, and in the denominator is the discretized volume value, delta k, sorry, delta k cubed. And so again, we need to change variables that we do here. And if you followed here, the calculations are much simpler because we don't have modes now. And so we end up in the end with this result here, where the density of states for a 3D structure is a continuous function of the energy, and the exact form is actually that of a square root of the energy. So overall, if we put everything together, we can see how all these density of states function compare. So we started with the blue one that is for a 1D structure, then we have the green one for a 2D structure, and the red one for a 3D structure. For clarity, I've also put here the case of a 0D structure that is not really a function, as we said, but is a completely discrete now type of function. So it's just localized at one energy, as we've seen. So for 0D structure, we are expecting only this state available with some degeneracy, this state available, and this state available, and so on and so forth. Oh, we should keep in mind, though, that the confined dimensions play a very important role on how these three different cases we've analyzed compare with each other. If we consider a 1D confined structure, but we drop the condition of being, for example, heavily confined in X and Y, then what happens is that this 1D confined structure will start to resemble a lot the 3D structure, at least for what concerns the density of states. And that's what exactly these two graphs here are trying to tell us. So here on one side we plot the density of states for a 1D, 2D and 3D structure when one or more of the dimensions that have been confined has a size of 20 nanometers. So in the case of 1D structures, this means that the two other dimensions that are confined have a size of 20 nanometers. So this is a wire, if you like, that has Lx and Ly 20 nanometer. In the case of a 2D structure, the one dimension that is confined has a size of 20 nanometer. Now, if instead we relax a little bit this condition and we make the confined size 100 nanometers, suddenly we can say that the 3D density of states, the 2D density of states, and even the 1D density of states overlap quite well. And it's very, very difficult. It starts to be very difficult to distinguish between them. So this emphasizes once more the fact that it is only when we are in the nanoscale that interesting quantum mechanical phenomena start to become evident. Let me just point you out an important detail here. So as you can see in these graphs, the density of state is shown as a function that has the units of centimeter to the -3 and eV to the -1. Now, the density of state that we've calculated, if you notice, is actually the density of states for the entire piece of material, is not per unit volume. So this means that what is being shown in these plots is effectively the density of states that we've calculated previously, whichever it is, either the 3D case, the 2D case, or the 1D case, divided by the volume of a piece of material we're dealing with, where the volume V is, according to the formulas we've used, is Lx times Ly times Lz. Okay, another important phenomenon we should discuss, which is obviously related to these things we are exploring, is the quantum of conductance. So consider this situation. Take a piece of material like a wire and imagine to scale it down into the nanoscale. What do you think will happen to the resistance or the conductance of this nanowire? So let us try to understand what will happen. Let us start by looking at what happens first of all in the bulk. So here we will basically have a look again to Ohm's law from a different point of view, but we'll see the result is exactly the same. So in the bulk, what happens when we apply an electric field to a wire, for example, a conductor that is a cross-section A and a length L? Well, the electrons tend to move in the direction of the electric field. They drift in that direction, but because they collide with the crystal, with the lattice, their movement is quite chaotic, and so they follow, they move in the way that I tried to describe here. Each arrow represents the movement of the electron as if it was a free particle until the next collision. And so between one collision and the other, the electron travels a distance that we call lambda m, the mean free path. And between one collision and the other, the time that the electron spends accelerating under the effect of the electric field is tau c, that we call the coherence time. So if we analyze this problem classically, we use Newton's law, and we use the fact that the force applied to the electron is due to the electric field, and also the acceleration could be estimated simply by dividing the final velocity that we call VE of the electron divided by the coherence time tau c. Then we can, from this equation here, estimate maybe, which is the final velocity of the electron before the next collision. And we can see that this relation is actually a relation between the velocity and the electric field. But we've already seen that this relation is exactly that one that defines the mobility, which means that through this very simple analysis we can define the mobility as a function of microscopic quantities like tau c and the mass of the electron. So this is a very nice little formula to obviously remember. So if we now use our result that J is equal to the density of electrons time the charge of the electron time the velocity, then we can write J in this term. So J is related to E in this way, which allows us to define the resistivity. And this is basically the part that we, in a way, came across already some time ago. That is basically the Ohm's law. And here we can see similarly the relations for the conductivity sigma and the conductance G. So here is now the point that we should concentrate on. So if we look at this relation for G, it would seem here that L, remember, is the length of our conductor. So from this relation it would seem that if we decrease L, we could potentially make G indefinitely big. And this is not the case, at least not once we enter the nanoscale. And that's what we will discuss in the next few slides. So what we are about to discuss is something that is true for confined structures. So in principle is valid for 2D structures and 1D structures, but it is much more easily identified in 1D structures. So for this reason, we will consider in our analysis 1D structures. So let us consider our confined 1D structure. That is this one here is let's say a nanowire. The confined sizes are L and L, and which corresponds to an area of L squared. And the length of this piece of material is L capital. And we imagine to apply a voltage across this piece of material in the way that I've shown here, and by creating some contacts between our external circuit and the piece of material. So here we need to do now some assumptions in order to continue our analysis. First of all, we will assume that the contacts we've just made are reflectionless. Now, the reason I'm saying this is that we've seen that if charge carriers, electrons, have a barrier in front of them while they propagate and they hit this barrier, there is a chance that they can tunnel through, but there is also a chance that they are reflected. So by saying that the contacts are reflectionless, we are actually saying that the presence of these contacts do not add any barrier to the propagation of electrons. The second assumption is that there is no scattering. So unlike the case that we've seen previously in the bulk, where we have scattering, and scattering dominates everything in that case, in this case we will be working under the assumption that we have no scattering. And the way to say that is that the length L of our piece of material is smaller than the mean free path of our electrons. This condition is called the ballistic condition. And just to have an idea of how much is the mean free path of free electrons, we can have a look of free electrons in a conductor. We could have a look at this universal curve that is here. So we can see that, for example, at 1 eV, the mean free path could be of the order of 100 nanometer. So it depends on the energy, obviously, of the electron. So for small energies, we have quite large mean free paths. And so this means that we can enter a ballistic condition when the size L of my piece of material is comparable to that mean free path. The last condition is that the thermal energy is smaller than the separation arising from the discretization of the energy levels between the bands. So the separation between the bands in our material, the discretization of the energy levels has to be bigger than the thermal energy, so that this phenomenon can be observed. The phenomenon we are going to discuss can be observed. So let us consider two situations. The first one, the potential difference between the two contacts is zero. So because this is a single piece of material, we should expect that the Fermi level on the left and the Fermi level on the right are effectively aligned. if we wanted to be even more precise, we could sketch the EK diagram for our 1D structure, for example, made of two bands as I've done here, and if this is the Fermi level, which is the same across the entire device, and so both in the left and both in the right, then in blue here I've shown the states that are filled with electrons. So the states are all filled up to the same level, both on the left and both on the right. So no electron can move because there are no available states to move to at the same energy level. Now, things change when we increase the voltage. So if V now is, for example, bigger than 0, what happens, as we've already anticipated and we've seen some time ago, what happens is that the right-hand side is pulled downward because of this voltage applied. And so this means that there is now a difference between the Fermi level on the left and the Fermi level on the right, which means that the bands on the left and the bands on the right are filled to different points. So in blue again, here I've drawn the states that are filled on the right, on the left and on the right. And as we can see, on the left, now there are states that are those that I've highlighted in green that could move toward the right and occupy the states that I've highlighted in green, in dashed green, that are free, and so can be occupied by those electrons from the left. Oh, please note that only the electrons that I've highlighted here with the green can move toward the right. And the reason is that they possess a positive kz. Remember that a positive k value corresponds to plane waves that are moving in the positive direction of the axis, while negative values of k correspond to plane waves that move into toward the negative side of the axis. So that's why we only those highlighted in green can move toward the right. So once we understand this very crucial point, we can now start thinking of calculating the current flowing through this conductor. So we want to calculate the relation between I and V, as we did when we, in the bulk case, calculated the Ohm's law. So again, as we did several times now in the previous slides, we should consider just one band for now. So let's take the generic one, Nx and Y. So we remember that the dispersion relation here is given by this function, and we should recall a quantum mechanical result that says that in quantum mechanics the velocity, the group velocity of a wave, of a particle, is calculated in this way. So this means that along kz, the velocity of my electrons is given by this quantity, which is obtained simply deriving the above dispersion relation. Now, when we were dealing with the bulk, we used this formula here, where VE was the drift velocity. Now, if we think about what we are doing here in this equation, effectively what we are doing is that we are assuming that all electrons that are represented by this density of electrons here are moving with the same velocity v. And this is the key point now, because now instead, in our case, our electrons that are sitting on those bands that we've seen before, they don't move at the same speed anymore. So by recalling that the density is given by the total number of electrons divided by the volume of the material, where the total number of electrons now is given by this formula here that we have seen in the previous section. So if we transform this integral in terms of k, because the speed of, in our case, the speed of the electrons is a function of k, so we will see that everything becomes much easier if we work in terms of k rather than in terms of e. So if we go back for a moment to the density of electrons and we transform these in terms of k, we know that G1dE has a very simple form in terms of k. We have highlighted this point previously. So we know that the density of electron is an integral over kz. And the velocity of our electrons depends on kz. This means that unlike what we did in the bulk case, here the velocity of the electrons have to be inside that integral and integrated over all possible kz values. And so this means that J must be calculated in this way. So we are basically following what we've seen in the bulk case. So we have the charge, the velocity, and an integral that relates to the density of the electron. But the velocity has to go inside the integral because each electron, each different kz value has its own velocity. And so we are basically ending up with this formula here for the current density in our 1D structure under a certain voltage V. Okay, this is all very general yet. And to make it more specific, what we need to now realize is that electrons in principle can move from left to right, but there may be also some electrons that move from the right to left. It depends on the available states they see in front of them. So in order to calculate this current here, what we need to do is that we need to integrate only on the kz values that are positive. So the integral goes from 0 to plus infinite, because these are the only electrons that are moving from the left to the right according to the to the reference system we've used in the previous diagram. And so similarly, to calculate this current here, we need to consider only the kz values that are negative, because these are the only electrons that move from right toward the left, toward the negative side of the kz axis. And so in reality, the total current is given by the sum of these two components, two parts. And the reason we are doing this is that now this can help us simplify a little bit things. Oh, please note that by doing this thing here, we have also introduced EFL into the Fermi function of the first component there, and EFR into this one. Okay, this is obviously because the electrons that move from left to right start from the left, and so they the Fermi function has to contain the Fermi level on the left, and similarly for the other component. So at this point, what we have to do is to note that the dispersion relation EKZ is symmetric with respect to KZ, while the velocity of the electron is antisymmetric, as we've seen a few slides ago, because it's a function of Kz. So if Kz is negative, the velocity becomes negative. So we can use these two observations to say that of the two integrals, the one related to JRL, so this is the integral that is related to this current here, that goes from minus infinity to 0, actually is equivalent to minus this integral. And the reason is because of the fact that V is antisymmetric. So when Kz from negative becomes positive, because here we are dealing with an integral that is now between 0 and plus infinity, so Kz is positive values, V will have changed sign. So in order for this to remain an equality, we need to put here a minus. And so having understood that, we can rewrite now the total J as this single integral here from 0 to plus infinite, and with these two now Fermi functions, one related to the left and one related to the right. At this point, we would like to change variables and go from Kz to E. So we change also the extremes of the integral, and we start changing here the integration variable from Kz and E, and so we get to this point here. So V, thanks to the change of variable, has been simplified. This is a very important point now, actually. And so as we can see, finally, the final result is independent from the velocity anymore. And there is only this integral here that we need to calculate. So just to make things a bit simpler and be able to do the calculations here, let us assume that the temperature is 0. With this assumption, basically what we are doing is basically we are saying that the Fermi function is 1 up to EFR for the case of the right electrode, the right side, and while is 1 up to EFL for the left side. This means that the previous integral can be now specialized in this way. We need to break it up because now the two Fermi functions become R1 in a different region in energy. So that's why we need to break up the previous integral in this way. And so the calculation can continue quite simply, and we end up to this point here. And finally, through very simple simplifications, we write J in this way. Now we should recall that I is J times A, and so we can relate finally I with V through this chain of equalities. And so we have that I is 2E squared over H times V, and we call this quantity here G0, which we call the quantum of conductance. So what is remarkable here to see there is that I and V are related by this constant here, but this constant, unlike the case we've seen in the bulk, Ohm's law, is actually independent from the geometry of the structure we've considered, the 1D structure. And also is independent from the mode or the band that we considered. So this is quite a remarkable result that we are obtaining in the nanoscale. If we transform G0 into a resistance, so R0, it corresponds to 12.9 kilo ohm. If we now drop the assumption relating to the contacts, and we assume that the constants are not perfectly reflectionless, then what we have to do is simply to add to our formula for G a factor that takes into consideration the tunneling probability through whatever barrier the contacts are creating for electrons that are in the band that we've considered. So we could consider this term, this factor named T, and X and Y. And if you consider that in general we have many more bands than just one, than the one that we've considered until now, then the most general form for our G is this one here. Please remember that this result is really valid only at T equals 0 Kelvin. And note also that this sum again is done over all the quantum values of an X and then Y, such that the corresponding energy E and X and Y is smaller than the Fermi level on the left, or anyway the bigger of the Fermi levels, EFL or EFR. In order to be able to appreciate fully the implications of this formula here, we should have a look at the quantized energy levels in our quantum wire, and that's what we do in this slide here. So I've written down for you the term in the energy of the system that depends on just on the quantum numbers nx and ny. And if you look into our notes, you will see that the expression for this term is exactly this one here. Oh, remember that we are talking of our nanoscale wire, our nanowire, where we have the confined directions X and Y, where the size of the piece of material is L in both directions, while the length of the nanowire is capital L. And we said that we are working here under the assumption that while the dimension in X and Y are confined, the dimension in Z is such that is smaller than the mean free path of the electrons. So just to remind you also these assumptions that we are making here. So the dimension in X and Y are the same, and the system is confined in these directions, and the dimension along Z is capital L. So under these assumptions, and considering that, remember the reference system is as I've drawn it here, then we can rewrite very simply these quantized energy states as a constant time something that depends on the quantum number, so nx squared plus ny squared. So this means that if we calculate these the first few energy levels, we could get the following values here. So for nx and ny equal to 1, we get the state E11, which is the constant, up there time 2, and the 2 comes from the fact that for an x equal 1 and then y equal 1, this quantity here will give us 1 squared plus 1 squared equal 2. We can repeat the calculation for state 1, 2, or 2, 1, which will give the same exact energy. So we call it E12, and is again the constant time, this time 5, because 1 squared plus 2 squared is 5. Oh, remember that here I'm writing down the degeneracy of this state. Sorry. So for E12, the degeneracy is 2. There are 2 states with the same energy. And then we can go on with 2, where the energy E22 would be the same constant time 8. The constant is calculated here, and remember that the constant is h bar square pi square over 2m time 1 over L squared. Now the first factor is made up just of constant values, and if we assume that the mass of the electron is effectively the rest mass in vacuum, we can calculate the value of this first term here, and the value would be this one. So we can now create a table where we could calculate the value of this constant in EV for several values of L, because the constant obviously depends on 1 over L squared. And so we get some values here, and this allows us to calculate for each of these values of L. Remember that L is the confined dimension of our nanowire. So we can calculate easily then that the value for E11, E12, and D22 for the first energy levels for those values of the dimension L. And we can see that effectively for L equal 1 micron, these energies or the first few levels are extremely small. And these are in terms of EV, so you can see that for L equal 1 micron, the energies are in the 10 to the minus 6 EV. For L equal 100 nanometer is in the 10 to the minus 4 EV. So it is only when we consider values of L below 100 nanometer that the corresponding energies E11, E12, and E22 could become observable maybe. So we can see, for example, that for L equal 10 nanometer, E11 would be 76 millivolt, 76 milli-electron volt. E12 would be 190 milli-electron volt, and D22 304 millielectron volt. Remember that in order to have a feeling of how big are these numbers, we should always compare these values with the thermal energy, KBT, which, if you remember, is around 25 millielectron volt. So we really can understand now that it's only when we are, well below 100 nanometers that these energy levels start to acquire observable values. So we are now in position to understand a bit better how would look like the energy diagram of my piece of conductor, of my piece of nanowire, when the wire has a confined dimension L of different size. So for example, when L is 100 nanometers, we could expect that the first three bands are effectively overlapping over each other, as I tried to do here. And this is because E11, E12, and E22, and so on, are all extremely small values. And so they lie very close to the zero of the energy, basically. So this means that if this is my Fermi energy, the bands that are below this Fermi energy are, say, n bands. And so the total conductivity of this relatively big nanowire would be this one here, n times G0, where n is the total number of the bands that find themselves at least in one portion below the Fermi level. As you can see here, so 1,1 has a degeneracy of 1, 1,2 has the degeneracy of 2, and 2,2, for example, has a degeneracy of 1. So in order to obtain n, I need to consider the degeneracy of those states also. And when we move to a much thinner wire, so we have decreased the size L further, now it is 10 nanometers, we could imagine that we are in a situation as this one here. So now the discretization is much more evident, because now, if you remember, the E11, E12, and E22 are effectively observable because they are bigger than the separation between them is bigger than the thermal energy, for example, at room temperature. So E11 would be 76 millielectron volt, and so on. So we could imagine that the band, the energy diagram in this case would look something like that. So if this is my energy, Fermi energy now, we can see that the bands that would be involved in conducting some current through this piece of conductor are those that are below the Fermi level, and so is effectively bands 1,1 and 1,2. Considering that band 1,2 has a degeneracy of 2, so there are effectively 3 bands that lie below the Fermi level, and which means that the total G of my system is expected to be, in this case, 3 times G0. If we shrink further the size of my nanowire with L now equal 1 nanometer, we could expect that because the discretization is now even more pronounced, that only the first band now is effectively below the Fermi level, and so the conductance of my system is effectively just G0. So this is telling us effectively that in the nanoscale, if we were to plot G in units G0 as a function of the dimension of the nanowire along the confined directions, we would be able to see that the resulting curve would look something like that, a step function that changes abruptly when L acquires a certain specific value. And each step corresponds to another band that becomes available and falls effectively below the Fermi level. We should look at this result in the framework of the general result that we know from the bulk. So if we go back for a moment to Ohm's law, we know that the conductance of a piece of material is obtained by the inverse of its resistance, and from Ohm's law we know that this can be written as 1 over rho, where rho is the resistivity of the material, time the cross-section area of the material divided by L capital, which is the length of my piece of conductor. So we are still obviously using the same formulas basically as for the nanowire. So we are saying that this is the cross-section area, this is the length of my wire here, and again we can call this L and this L, and so we can say that the area is again L squared. So if we were to plot in the bulk case G as a function of L, then we would expect a parabolic behavior. And on this plot, the nanoscale is actually whatever is down here. So what we are saying basically in these slides is that the bulk is telling us that the relation between G and L should be parabolic, but when we approach the nanoscale, effectively G becomes quantized and assumes this type of behavior. Okay, let us discuss now another important nanoscale phenomenon, which goes under the name of Coulomb blockade. This phenomenon originates from pure electrostatic effects, and in order to explore this phenomenon, what we have to do is to consider a spherical object that we will call a dot. Let us assume that this is a conductor and has a spherical shape with a radius r. Then electrostatics teaches us that the capacitance of this object is given by this formula. And the energy required to place a certain charge on this object with this capacitance is given by this formula. So these results are at the heart of what we will discuss in a moment, that goes under the name of Coulomb blockade. And in order to understand this a little bit better, we will go into the details of the analysis in the next few slides. So, as we said, we are assuming that we have a conductor and it is a sphere with a radius r, and this is immersed in a medium with a dielectric constant epsilon ox. So the capacitance is given by this formula here, the capacitance of this metallic conductor, and if we place a charge Q on this conductor, then the energy acquired by the system is given by this formula. These are results that we have obtained from electrostatics. Or remember that epsilon ox is the dielectric constant of our medium around the capacitor, the conductor, and it is given by epsilon 0, which is the dielectric constant of vacuum, time the relative dielectric constant of the medium. And remember that epsilon 0 is a universal constant and has this value here. So let us calculate the capacitance and the charging energy of our conductor when we place one electron on it. So on this table I've summarized some examples here for R equal 1 micron, 100 nanometer, 10 nanometer, and 1 nanometer. So we can see that, for example, for if the radius is of this dot is 1 micrometer, then the capacitance is 10 to the minus 16. And so the charging energy is extremely small, and in terms of EV corresponds to basically 0.7 milli electron volts. It is only by reducing the radius of this dot that we can say that this charging energy starts increasing. So for 100 nanometer, the charging energy becomes 7.2 milli electron volts. At 10 nanometer radius, the charging energy is now 72 milli electron volts. While if the radius was 1 nanometer, the charging energy would have been 0.72 electron volt. So quite a large number. Remember that we need to compare these numbers with the thermal energy, kT, which at room temperature is around 25 milli electron volts. So we understand that when we are in the nanoscale, so let's say below 100 nanometer radius, then this charging energy becomes comparable or bigger than the thermal energy at room temperature, and so the Coulomb blockade phenomenon could become macroscopically observable. We should also remember that all these numbers in these tables are obtained for just by charging the system with one electron. If we were to charge the system with more electrons, then the charging energy would be even much bigger, as we see here. So if we were to charge the system with 2 electrons instead of 1, then the charging energy would be 4 times the values we've just seen here, EC1. If it was we were to charge the system with 3 electrons, then the charging energy would be 9 times the values we've seen here, AC1. So depending on the number of electrons we place, the energy of the system could change dramatically and become obviously observable macroscopically. In order to visualize all this properly, we can draw this energy diagram here, and in red we've drawn our quantum dot, our sphere. So in the first diagram here on the left, we are in a situation where obviously there is no charge, and so the energy of this system, because of the charge it has, is effectively 0, EV. So when we place now one electron, what happens is that the energy of the system becomes EC1. Whatever EC1 means, it depends on the radius of the dot, as we've seen. So the system moves to this point here, which is the energy, is what we call EC1. So on this energy axis, EC1 is our unit effectively. But when we move, we add one more electron, so the total charge on the system is 2e, then the total energy of the system is effectively becoming 4 times EC1, and so the system, the energy of the system on this diagram moves up to here, which is, as you can see, 4 times. So the jump by adding one more electron to our previous situation, the jump made is effectively this one. So 3 times EC1. If we now add one more electron to the system would go from this point here, which was 4 times EC1, to 9 times EC1. And so this would be the jump. So as you can see, well, here was the initial jump was this one here. So every time we add one electron, the increase in energy of our system is not proportional, obviously, to the charge, but as you can see, becomes larger and larger. So when we've added one electron to the system, the delta E was equal to EC1. When we added the second electron to the system, the delta E was 3 EC1. And then we added the third electron to the system, the delta E was 5 EC1. What we just said explains in physical terms what the Coulomb blockade is. Now, together with what we've just seen in terms of energy acquired by our quantum dot, we should also remind that for these charging energies we just described to become effectively measurable or observable macroscopically, we need our quantum dot to effectively be in the nanoscale. And so we need to add an additional layer of complexity to what we just said, because we know that if our piece of material is in the nanoscale, which means that it is confined, then we need to take into account the confinement. And so if our spherical piece of material is in the nanoscale, then we could model it as for simplicity as a cube like that, and this is actually a 0D structure as we've seen in our previous slides. And so basically we have to expect confinement in all directions. This means that our quantum dot could be modeled using the approach we've seen previously in our slides, and so could be seen as an infinite potential well in all 3 directions, x, y, and z, with a potential given by this type of shape here, where V0 is extremely high, let's say, it tends to infinite. Or in the next few slides, we will assume, for simplicity in our analysis, that all 3 dimensions, L, X, L, Y, and Z of our cube are the same. And so we should remind then ourselves that the eigenvalues of our Schrödinger equation, the eigenvalue equation here in this system, is given by this formula, where we have L is this common dimension of our system, and we have emphasized the dependence on the 3 quantum numbers nx and y and then z. So we could rewrite the eigenvalues of this system as a constant time, something that depends on nx squared plus ny squared plus nz squared. Obviously here we are now revising something that we've seen a few slides ago, just expanding it a little bit and to adapt it to our needs for this analysis regarding the Coulomb blockade phenomenon. So the formula we just seen allows us to calculate quickly the first few energy levels of this infinite quantum well, 3-dimensional quantum well that represents a 0D structure. So for example, the ground state is represented by the combination of quantum numbers 1, 1, 1, which gives the ground state, which we will call E0, equal to the constant we've just mentioned, time 3 because obviously nx squared plus ny squared plus nz squared in this case gives 3. And so if we keep going, the next state on the energy scale would be given by the combination 1, 1, 2, and this is the next available state, so it would be E1, and this is the constant time 6 now, just because nx squared plus ny squared plus nz squared in this case would give 1. And remember that here we are writing down the degeneracy of each one of these states. So how many states have the same energy. So in this case of E1 we have 3 possible states because we have 3 possible combination of these quantum numbers that could give the same energy E1. And same story for E2, and so here the energy would be the constant time 9, and again we have 3 states. We should now try to realize the actual value of E0, E1, and E2. And in order to do that, we should remember that the constant that is in front of these numbers here is actually a function of L, as we've emphasized here. So in order to do the calculation, let's calculate first the term h bar squared pi squared over 2m, assuming that instead of n we use m0, which is the mass, the rest mass of the electron in vacuum. We remember that h has this value here, and so we calculate the constant term, and then we have to take into account the term concerning the actual size of the system that is taken into account by this term 1 over L squared. So we can create this table here, again similar to what we've done previously with the capacitance and the charging energy. So let's take L equal to 1 micron, 100 nanometer, 10 nanometer, 1 nanometer. Just to get an idea of what we should expect. Here are the values corresponding to the constant, this constant here for dose L, and so by using the expressions we found here above for E0, E1, and E2, we can finally calculate the corresponding E0, E1, and E2 for these specific values of L. So at 1 micron, E0 would be 11.4 10 to the minus 6 eV, E1 would be 22.8 10 to the minus 6 eV, and the E2 34.2 10 to the minus 6 eV. So we can see that for 1 micron, but also for 100 nanometer, the 3 states are extremely close in energy and very small, very close to the zero. It is only when we move into the nanoscales or below 100 nanometer sizes that we see that E0, E1, and E2 start becoming measurable, and by that I mean that they start becoming larger than the thermal energy at room temperature of 25 milli electron volt. So for example, at 10 nanometer, E0 is 114 milli electron volts, E1 would be 228, and so on and so forth. So we are in a situation that when we consider our spherical capacitor and we say that the charging energies have to become appreciable in order to be able to observe the Coulomb blockade phenomenon, we need to keep in mind also that in order to achieve that, most probably we will be in confinement conditions, and so we will also have the discretization of the energy levels in that piece of material. So effectively we need to remember that the accessible states for any electrons are those here, okay, discretized. So this is a very important detail that sometimes, if you look at Coulomb blockade, could be missed. Okay, always remember that if the charging energy becomes appreciable, it's very likely that we are in extreme confined conditions, and so the discretization becomes very, very important. The discretization of the energy levels becomes very, very important. So let's go back to our Coulomb blockade phenomenon. Now that we've understood the physics behind it, so we would like to go back to this diagram here that effectively allows us to see in practice, in action, the Coulomb blockade phenomenon. So what we have here is a very simple circuit that I've redrawn here in this way, just to make it a bit clearer. So this circuit is made by a tunneling junction where electrons can tunnel in this way. We have our quantum dot, our spherical capacitor, and then we have a capacitor here to close the circuit. Now, this is an equivalent circuit of a real circuit that would be actually made in this way. So it would be made by creating an electrode, generally made in this way, for example. Remember that we are talking of things that are in the nanoscale, so these are obviously all very small electrodes. So we have our left electrode, we have our right electrode that correspond to the wires, if you like, in our equivalent circuit. Between these two electrodes we have applied our voltage, and now we have between the edge of this electrode and the quantum dot we have our effectively tunnel junction, so electrons tunnel through this separation here, and then we have on the other end effectively another separation that acts as a capacitor. For what we will see in a moment, it is very important that we realize that also this end here could act as a tunnel junction, and actually we will see it later on. So it is very important to tune these separations properly so that effectively the tunnel probability is high here and not so high here. Okay, so this end here effectively works just as a capacitor, while this other end is effectively our tunnel junction. So in this situation, and reminding that we are in extremely confined conditions, so that the energy levels are quantized and so on and so forth, we could attempt to draw the energy diagram of this system in the way that I've done here. We could assume, for simplicity, that the electrodes and the quantum dot are all made of the same material, so that we can draw it in this way. So this would be the Fermi level of the electrode on the left. And then we have the tunneling junction, which is this represented by this barrier here. Or we could imagine that we are in vacuum. And so the tunneling junction has corresponds to a barrier that goes up to the zero of the energy in this case. So we said that the zero of the energy corresponds to the vacuum level, as we said. And then we have the dot with quantized states, and then another barrier that is represented by the capacitor that we've seen on the right hand side, and finally the a Fermi level of the right electrode. So this is the energy diagram depicting the bands of my circuit. So let us see the Coulomb blockade effect in action. Let us assume that initially the charge in our dot is 0 and that the potential is 0. So the energy diagram is flat, as I've drawn it here. And so if there was an electron on the left hand side could potentially want to tunnel through the tunnel junction, it wouldn't have a state to tunnel through because the first available state is slightly higher than that, and so it's not accessible to that electron. This means that I need to now increase a little bit the voltage up to a value V1 positive. This means that by applying a voltage, I'm effectively pulling down, as we've learned now, I'm effectively pulling down the right side of this diagram. This means that I'm effectively also pulling downward the entire diagram. So at a certain point, the first energy level, quantized energy level of the quantum dot becomes aligned with the Fermi level of the left injecting electrode, and so the electron happily can move now into that state. Now at this point, as soon as the electron tunnels into that state, the dot, because it's very small, changes its energy by the amount EC1. And so as you can see here, now that the charge into the dot is become 1 electron and we are still at a voltage V1, the band diagram has changed because the quantum dot has increased its energy. It was down here, the quantum dot, but now has moved upward by an amount equal to EC1, the charging energy due to the fact that we've put 1 electron into the dot. And so now if there was another electron ready to tunnel into the system, it wouldn't be able to tunnel because there is a mismatch here, and so there is no state it can tunnel through. The first available state is slightly higher than the energy from which this electron is tunneling into the, or would be tunneling into the system. So this means that in order to allow a second electron in, I need to increase the voltage beyond V1. So I need to go to a voltage, for example, V2, slightly higher than V1. And so this is represented by this, you can see here, we have to pull slightly more down the system until we drag also the dot enough low down now that it aligns again its first available energy level with the electron, and so the electron can tunnel finally into this state. Or remember that each state can accommodate 2 electrons due to spin degeneracy in this case. And so we end up with 2 electrons now into the quantum dot. This means that now the dot will increase even further its energy, because now we are going from the situation where we have 1 electron to 2 electrons, and we know that the jump in energy will be 3 times EC1. And so the new band diagram in this situation, when we are now still at voltage V2, is now like that. You can see that now the quantum dot has moved even more upward than the previous case. And the reason is that now we have 2 electrons into the quantum dot. And so if there was here another electron ready to tunnel, it wouldn't be able to, because obviously there is a mismatch and there is no available state at that energy level. And so again, the story goes on. We need to increase further the voltage in order to allow a third electron. Actually, for the third electron, we have to actually increase the voltage such that the alignment between the Fermi level on the left happens with the second quantized state, because obviously the first quantized state is now full. That's why it is important, and I wanted to stress that it is important to remember that there is also quantization of the energy levels in the quantum dot. And so to conclude this exploration of the Coulomb blockade phenomenon, we could draw a diagram of the charge in terms of in units of electrons in the quantum dot versus the voltage we've applied to this hypothetical circuit. And so we would see that initially the charge is 0 at very low voltages, and then at a certain voltage V1 we are able to inject an electron into the dot, and then we need to reach a voltage V2 to be able to then increase the charge to 2 electrons, and then a voltage V3 to get a third electron in, and so on and so forth. I would like to stress here the importance of tuning properly the distances between the electrodes and the quantum dot, because we've said that we want this end to act as a tunnel junction while this end is simply working in that circuit as a capacitor. And the reason this is important is because, as you can see, by charging the quantum dot and as we move to higher voltages, effectively what is happening is that there is an increasing electric field on the right-hand side of our diagram. Remember that the electric field is given by, in this case, and remember that here what we are plotting is effectively the potential energy, so is related to V. So we do know that if this electric field increases too much, we could then induce the electrons that are inside the quantum dot to actually tunnel out of the dot. Okay, so that's why I want to stress it again, it is very important to tune this device properly if we want to observe the Coulomb blockade phenomenon. Actually, using exactly this observation, we can use this type of device configuration to actually create a device that acts as a single electron tunnel junction. So it allows only one electron to go through it at each time. And if we understood how the Coulomb blockade works, then it is actually very simple to understand how our single tunnel junction work. Single electron tunnel junction. So we can imagine that we are dealing again with a quantum dot that is extremely quantized. So let us imagine that the first available level is up to here. And this time the two barriers are effectively two tunneling barriers. So using this similar approach that we've discussed before, so when the charge is 0 across in our dot and the potential is 0, then no electron can tunnel through. It's only when we apply a certain voltage V1 bigger than 0 that at a certain time, at some time T1, an electron tunnels into the first available energy level. And so when that happens, because of the charging energy acquired by the quantum dot, the quantum dot moves upward as I've drawn here. And so this means that if there was another electron that wanted to tunnel through, it wouldn't be able because there is no energy level available at that energy. But what can happen is that if now this barrier is tuned properly in such a way that the tunneling probability is high enough, then at this point, after some time, at a certain time, T2, then this electron could eventually tunnel out of the dot. And so now the dot becomes empty. If it becomes empty, its energy is lowered by the amount EC1. And so we go back to this band diagram now. Remember that we are still at V equal V1. And so Now, if there was here another electron ready to tunnel, at a certain time, T3, this electron tunnels into the available energy level there again, and the story goes on. And so effectively, this means that the current passing through the system has the form that I've shown here, where every spike in current corresponds to the transmission of just one electron. Or remember that all this happens always at the same voltage V equal V1. So this is a very nice device that allows the transmission of a single electron at each time and exploits Coulomb blockade phenomenon, and also obviously the quantization of the energy levels due to confinement. This concludes chapter 3. So thank you for listening, and I'll see you next time.